Today I'd like to present Universal Entropy, Part 1. And in this we will, as a voyage of discovery, recreate for ourselves the work of Rudolf Clausius, who in 1850 invented the concept of entropy with respect to classical thermodynamic systems. And we'll also reproduce the work of Claude Shannon, who in the 1940s, working on coding systems for binary communications, such as, for example, sending a paragraph of the English language as binary bits. He wanted to know what the most efficient coding systems were for such communications, and he had to, in order to, to solve this, he had to extend the work of Rudolf Clausius from classical thermodynamic systems like gas and pistons and that sort of thing into the area of information theory with binary bits and encoding messages thereof. And in part 2, we'll also reproduce some of the work of John von Neumann, a brilliant mathematician in the 1950s, who developed an extension of entropy theory to encompass quantum mechanical systems, including, for example, qubits, which can be used to compute information and to transmit information as well. So with that, let's dive in. I want to talk about two links here shown. The first one there is where as a sort of tutorial to make people very at home with ln x, for example, in the top link. I derived that ln x is equal to the integral of dx over x. In other words, 1 over x dx integral. I show that in a complete derivation, simple derivation. Why that's equal to ln x. And in so doing, it makes the fact that that's so from being out there into, inside your own being and in a very real sense. You're in control of it. You're in charge of that. Your own version of ln x is equal to the integral of 1 over x dx. Also, in this second link, I helped make a tutorial deriving the geometrical meaning of the number e. In fact, we actually derive the number e in that video and show what e to the j means from a geometrical point of view. So my preference for proofs are to use approaches that do not require a lot of mathematical notation, and that allow you to basically look at it and see what's happening and encode that kind of deep understanding in a simple way, as simple as possible, and concise and comprehensive. That's what we're trying to do in these two videos, and it's what we're doing here today. And as a voyage of discovery, we're not going through and seeing pedantically what these forefathers of entropy did. We're basically just looking at what the topics we want to produce understanding in, and basically just through ordinary, very lay type person reasoning processes, being able to create the expressions and solve some problems. Basically, why should we let these guys who originally came up with these wonderful theories, why should we let them have all the fun? By allowing ourselves to delve into this and learn as a voyage of discovery, we can experience some of the original thrill that these thinkers were able to enjoy, and I want to help share that type of process with you here. So let's see now. As you can see, there's part 1 and part 2, and we're not going to do part 2 today because I want to get through this in a reasonable amount of time with you. But these black bullets in the top there, part 1, I'm going to go through before every section and talk about each point. So I don't want to go through it right now because as a matter of being timely. Okay, so the first thing is we're going to do something interesting. We just look at, remember the two videos I showed you, the tutorials on, one is on e, deriving the number e and what it means, e to the x, and that sort of thing. And one of the things that you notice, and I'll get my handy arrow up here, for independent events a, b, and c, which represent probabilities, independent probabilities, it is true that p of a plus b plus c is equal to p of a times p of b times p of c. And that's great and everything. But also of interest is e to the e, now the number e, which basically is just 2.7218218, and goes on like that. It doesn't continue repeating for more than a few times, and then it becomes a rational number of sorts. Anyway, it's a particular number, and we derive it in that link I showed you earlier. Anyway, e to the a plus b plus c is equal to e to the a times e to the b times e to the c. So it's a very, there's a lot of symmetry between how these two functions, the probability function and the exponential function, treat the items that they're operating on. And exponentials is the exponents, and for p it's the probabilities. So the way my mind works, I have an undergrad degree in mechanical engineering and a master's in electrical engineering and a professional engineering degree. That's sort of more than saying that's where I get all my information from, the education. It more speaks about a predisposition. And my predisposition is to model everything, and I've been doing that, my whole life. Just if I look at something, automatically my mind models it. And looking at these two functions here, the probability function, the exponential function, I see that there's a lot of symmetry there, and we should be able to represent probabilities in terms of exponentials. And so that's what we're going to explore right now as the first step. So I have here, solve p of x is equal to e to the x. Like, what is the solution to that? Well, I'm going to show you one here which at first will probably look strange, but when you see it, especially if you understand the natural logarithm, it should be, when you see it, it should be kind of like a horse kicking you in the head. It's like, of course. So the answer is kind of obviously p of x is equal to e, in terms of the exponential function e, is equal to e to the ln p of x. And how the heck do we know that? Well, we know that the job of e is to be the anti-function of logarithm, log natural. So it's the e is the anti-function of log natural. Some people call it the inverse function. Same thing. Which means that when you do e to the ln of x, x comes out. And in this case, x is equal to p to the x, p of x, probability of x. So p of x is equal to e of ln of x. That's the answer. And so you go, I say, well, gee, that's interesting. Is there any physical system that we can tie this down to? Because who cares about little mathematical things? But as a modeling exercise of something in physical reality, yeah, that becomes very interesting. So here I'm doing the bullet thing again. We're going to seek, red arrow, seek an application for the resulting answer. P of x is equal to e to the x. Which is ln of p of x, e to the x is, e to the ln of p to the x. to a situation in physical reality. So we're going to take that answer and see if we have a system that would in physical reality have ln of x in it. So I'm going to show you one. And here I kind of created this it's a variation of system that other people have used as explanations. However, the particular implementation here is my own. There's a piston in the, get my red arrow. There's a piston here with the gas in it. And it's sitting on a plate where that's kept at constant temperature. I'm trying to be explicit. I will try to keep this up, like T constant. You know, it's a constant temperature. I'll call it T constant. Later on, I abbreviate it to T sub C. You know, so you know what the heck I'm always talking about, because it's important that this temperature is constant. So what happened? And here this is a graduated cylinder filled with some heavy liquid. I'd say mercury, but it makes me think you're going to be poisoned by the thing. But let's say a liquid that's close to the density of mercury, and it's having little drops dropping out, which means this flask and it's a graduated cylinder, so you can see how much it's going down and work out how much it weighs, right? So you can calculate this whole process. But it's very important for what we're talking about now that the system keep the temperature inside the cylinder constant, and that it gradually reduce some of the work, lifting that graduated cylinder, and you can keep track of how much liquids come out, so you can know what the weight is, and it's just an experiment that gives you if you do it properly, a numerical answer of the work. The heat that goes in does a certain amount of mechanical work, and you can equate the heat to the mechanical work, and we're going to do that. So let's see, yeah, I'll explain that. Okay, good. So let's do the bottom statement here. As the graduated cylinder is gradually emptied by the dripping spout, the cylinder rises very gradually and the gas pressure drops. So the pressure, as the volume is increasing as this cylinder lifts, and the pressure in the gas is made by the weight of the rate as a force. So the force on this piston here, which is the weight of the glass plus the liquid, is pressurizing the cylinder. So as the flask gets, the graduated cylinder gets less and less heavy, the force gets less and less, and the pressure gets less and less. So we know the pressure is going down. Okay. As the cylinder rises very gradually, the gas pressure drops while the gas stays at the same temperature T sub C. So there we have it. There's our situation. Now let's see now. So we're going to derive the Rudolf Clausius thermodynamic formulation of entropy, quite a mouthful, in terms of both heat transfer at constant temperature and after that equivalently in terms of probability. So I'm always, Rudolf, sorry, yeah, it is Rudolf. I thought it was getting close to Christmas for a second. Reindeer. No, Rudolf Clausius. He did it first and came up with this expression in terms of the heat transfer. And then later, it was actually Gibbs, I think, who extended it to a same formulation, but in terms of probabilities. Now, I'm not so interested in the history because I want us to be the original, be just like the original explorers and go through this ourselves and have our own discoveries. And like I said, the excitement that goes with that. So here we're going to derive it, and in a different way, I think, than most people. And we're going to not assume anything, not take any information from anywhere. Anything we use, we're going to derive on the spot, just by looking at it. And that's another aspect of what I wish to communicate here is our thought forms, where you can just look at things and then start writing out the expressions. You don't need to go and look in a book, about what somebody wrote 230 years ago. You can just do it yourself. So let's do that. Some of that. So here we go. Let's derive the physical law that must relate the pressure in terms of the volume, okay, temperature, and the amount, and the constant proportion. Let's start with the pressure. Okay, now I'm relating, the next sentence is interesting. It relates it to what I like to do. We know we've amassed a lot of very, very useful information in our lives because we interact with physical devices. And so I say here, we know from pumping up basketballs and bicycle tires, etc., that the pressure goes up as we increase the amount of gas. So when you put more air in a tire, you know the tire pressure goes up. Okay. So so we know that the pressure P, and you know what? I'm going to do something that I normally do here, and I'm going to see if I can get this. Notice I have pressure here, and I'm going to talk about probabilities as well. Now, most people would leave that. So you have P for pressure and P for probability. And it's no time before you don't know which is probability and which is pressure. Well, I'm going to write it out, at least try to keep always doing it. When I do pressure, I'm going to write it P-R-E-S-S for pressure, so you always know which is which. Okay, so here I have here the first proportionality. As the pressure goes up, as the amount goes up, the pressure goes up. So they go up together, which means if you have any expression of proportionality, the amount needs to be in the numerator. If the pressure went down as the amount went up, you'd have to put the amount in the denominator, the bottom. But we're not going to do that because that's not our experience with bike tires, basketballs, and car tires. You put more in, and the pressure goes up. Okay, so pressure is proportional to amount. Very obvious for us. Now, and we're going to let amount be N, like moles, okay? So pressure is proportional to N. That's where we have it at the moment. So let's see now. The pressure drops as we increase the volume. We know that. For example, if you put air in a balloon and the balloon is made of rubber plastic and it stretches, the volume goes up, you know the pressure goes down. So we know that, and if you have a syringe and you just fill it with air and block the end and you push it in, you know the pressure goes up because you feel it, right? And when you pull the plunger back out slowly, you feel the pressure go down and down until the end. You don't even have to hold it, you know, as the end with the larger volume. So pressure drops as we increase the volume. So we know that that's one of those, it's opposite to what happened with the amount. As the volume goes up, the pressure goes down. Volume goes up, pressure goes down. You know you got to put the volume on the bottom. So we take the expression that we have so far, pressure is proportional to N, and we add the proportionality for volume. Pressure is proportional to N divided by the volume. So there we have it right here. So I haven't even told you what I'm not going to tell you. We're just interested. We want to know how the relevant variables affect the pressure, okay? So we've done amount and we've done volume now. What else is there? Well, temperature. Now we know that, and we're down here now. I'm going to move this away so I can get here. We're now we're talking about temperature. We know that if a car drives in the summer on the hot pavement, the temperature inside the tires, the outside and the inside, goes up, and the tire pressure raises, okay? And we know in a pressure cooker that when you turn the temperature up, the pressure in the pressure cooker goes up. It starts whistling like crazy. So we know that the pressure goes up as the temperature goes up. So in the proportionality, you have to put the temperature at the top, the numerator. You have to put the temperature in the numerator because they both go up together. Okay, so that should be pretty obvious. So now I have pressure is proportional to N, the amount times the temperature, divided by the volume. Now, let's see now. which you could divide, sorry, you could multiply in this second to last expression here of proportionality. You could multiply both sides by the volume, so you get pressure times, it's not important that we do that, but I want to put it in a specific form that's recognizable. So what we get then is pressure times volume. Now I'm going to also put R as a constant of proportionality, and in this case, since the amount was in moles, it's going to be joules times divided by kilograms times moles. Joules divided by kilograms times moles. And when we do that, applying the constant of proportionality, the expression we have before, which was just proportionality, turns into an equality. So we have pressure times volume equals nRT. So we just went back and derived the expression called the universal gas equation, which is true especially for ideal gases, where they bounce like little tiny balls and they don't interact too much together, and they don't stick and things like that. So an ideal gas. So we have the universal gas law there. And we just derived it by just very, very basic thinking. We're going to do that same kind of basic thinking to derive all the things that, well, not all of them, but the essential core of concepts that these great thinkers did. And I think that's how they really think. And when they write their papers, of course, they put in a bunch of notation and other things. I like to joke about such things, even though they are clearly great thinkers and they've made a great contribution. I don't want to really not appreciate what they've done. I do appreciate it. So I just switch charts now. It doesn't look so busy, but there's some really cool things that are going on in what I'm talking about here. So up here on the top, we have our pressure times volume equals N times R. N is the amount, moles, times R is the constant of proportionality times the temperature. In this case, T sub C, because taking the universal gas equation and applying it to the particular experimental setup that we just have, in which the temperature is constant. So I'm using T sub C now. And so we have the pressure is equal to N times R times T sub C divided by the volume. Okay. Now, here's where it gets kind of interesting, because I'm out of the blue bringing something that we know, and if we don't know, I'm going to kind of derive it anyway. So this is new. It's not from before. If you take the pressure, written press, as explained previously, and integrate it, you get the force. What is a pressure? It's a force divided by the area, okay, by definition. And dV, the change in the volume, is equal to force times the change in the length. Sorry, my arrow was blocking. Here it is. Pressure is force divided by area times dl is the change in the length times area. dl times area is dV, okay? And the force divided by area is pressure. So I've basically got the integrand there. And the area here, you notice it's force divided by area times delta L times area. The area is in the numerator and in the denominator, so it cancels. And you get force, this integrand here, is force times delta L. Okay? Well, that's force times a little bit of distance, and we know that force times distance equals work, right? So we got the work term we're looking for. And since the only energy going into the cylinder, the piston, is in heating up the gas, that it's the heat input, which we could call like, I think it was Rudolf Clausius who first started to use delta Q, the change in the heat that flows, okay? So this expression gives us the heat input at T sub C, going from the plate that's kept at the constant temperature, the heat migrates into this cylinder as the piston, as the graduated cylinder lifts because it's getting lighter and lighter. Okay. So now I'm going to do this handy dandy substitution. We already worked out the universal gas expression for the pressure. And we have the pressure in the integrand, okay? And the volume's going to be changing. So we can substitute for the pressure into this is, it's equal to N times R times T over volume. We can put that in for the pressure into this next integral here, which I'm doing. So we have this integral is equal to this new one where I take the pressure and I put something equal to that, which is nRTC and divided by the volume, and I take the dV from before and just put it back so where it belongs, and so we get this new integral. All right. Now, in our experimental setup, the amount, we didn't change the amount, so it's a constant. R is the universal gas constant, okay? And times the temperature, which is a constant. All three of those are constants, so they multiply to make another constant. We can take the constant out front because doesn't really participate in the integration very much other than what I'm doing here, N times R times T sub C times, and then this is the new integral, which is the same as the original one. And this combined with the constant equals the heat input at T sub C during the process of the liquid leaking out. Okay, so we have that. Now, in the links presentation about the natural logarithm of x, I would prove that it's equal to the integral of dx over x, okay? Now, in this case, dx is dv, and over x is equal to volume, which means that this integral is equal to nRTC times the natural logarithm of v2 minus the natural logarithm of, or v2 times, let's see, what is that? Yeah, the natural logarithm, well, the v2 times v1, and take that whole thing and do the natural logarithm. Now, as part of natural logarithms in general, and natural logarithms in particular, when you do ln of v2 minus v1, it's equal to ln of v2 divided by v1. It's just one of the features of logarithm. So we end up with this expression, very, very useful expression. nr times t sub c times ln v2 over v1 is equal to the heat input that transfers from that plate into the gas during the dripping of the graduated cylinder. So we have this expression. Now, it just turns out, I'm going to look at what's said here. It equals the heat input at dt sub c. That's equal to delta Q. It has a lot of very good information in it, and we should spend a little time to absorb it. We start off with the expression we derived in the last chart, and it expresses the amount of heat that's transferred from the plate into the gas as the gas goes from a volume of the initial volume to the V1 to the final volume V2, and we find that the negative the change in Q, and I'll have more to say about that, is equal to as we derived before, N, the number of moles, times R, the gas constant, times the constant temperature, and that times the natural logarithm of V2, the volume at the end, over the volume at the beginning. Now, and then I take the same thing, but you notice that the volume, we have ln V2 over V1, and we've established earlier that the pressure is inversely proportional to the volume. So the ratio of V2 over V1 will be equal to the pressure 1 over the pressure 2. And the constants of proportionality and the pressure between pressure and volume will cancel. So that ratio will be correct. So we get another something we're going to need in this chart, that NR ln pressure, the initial pressure and the final pressure, is equal to the negative the change in the heat over that's exchanged over at the constant temperature T sub C. Remember, we have a plate that's emitting heat into the piston chamber. And for the first time here, I define that the way that Rudolf Clausius did it around 1850 as a change in this quantity called entropy. Now, I want to settle this one thing point early, and maybe I'll repeat it even. It's very important. The energy leaves the plate, and by convention, that and goes into the piston. And by convention, that's they call that a negative. So delta Q is negative. And you notice that the definition of entropy says negative delta Q over T sub C. So it's really a negative times a negative, which is a positive. So the change in entropy is positive in this process. Okay, so that's an important point. Now here we come to we're talking about gases and classical mechanics, but we're going to be moving into discussing statistical mechanics, where probabilities are, these expressions can be expressed in terms of probabilities, entropy in terms of probabilities. And when we get to part 2, where we're talking about the quantum mechanical systems, we're going to be dealing almost exclusively in terms of probabilities. So in preparing the way, we need to be able to convert from these pressures in classical mechanics into talking about probabilities. So this next line I'm going to talk about is very, very special and important and germane to the conversion from talking about gases in terms of temperatures and pressures and states of a gas, converting it into probabilities. Now, I'm going to take pains in this presentation to, where I talk about pressure, I'm going to write it out, as pressures, P-R-E-S-S. And when I talk about probabilities, which we need to be able to do, I want to use P, just P. So you always know what's what, because I've seen what happens when you don't distinguish them so carefully. You end up being mixed up. You don't know whether we're talking about probabilities or pressures here. So now we say, for the special situation where the gas is expanded from an initial volume that's approaching zero, not actually equal to zero, where the mathematics goes crazy, but as close to zero as you want to get the accuracy more and more, okay? As you get so close to zero, the probe that you're using to detect the molecules, you keep that as small as you like, and the volume shrinks down. It turns out that the probe can occupy most of the volume, and if there's a molecule in there, the probe's going to be detecting it. So the probability goes up and up and up as the volume goes down and down and down. And at the where the volume approaches zero, the initial probability approaches 1. And then this expression here, pressure 1 over pressure 2. Pressure 1 then, sorry, I converted here to probability. So because we're going to want to talk about probability, remember. So now let's see, as the pressure gets greater, the probability gets greater, right? So they're going up and down in the same fashion. So we know that the probability is proportional to the pressure. So we can make a statement here that the ln of pressure 1 over pressure 2 is equal to the ln of the probability 1 over the probability 2. Now the probability 1, the initial probability, as the volume goes to 0, P1 is approximately equal to 1. So we can put in this expression above, which I'm going to repeat here, ln pressure 1 over pressure 2. The pressure 1 there is associated with a probability of 1. So you put a probability of 1 there, just put 1. P1 is equal to 1, or as close as you like. And P2 is on the bottom. That's this expression is going to be the same expression, in other words. So n times r times ln natural logarithm of 1 over P2 is going to be equal to the negative delta Q over Tc, which is an expression of entropy in terms of probability, where P2 is the final probability. So there we've made the conversion. We've been able to use this reasoning to make the conversion from classical mechanics, where they're talking about aggregate pressures, into statistical mechanics, where we're talking about individual molecules and the probability of the particular states in those molecules. So now let's see here. We have so at this point we're still using the classical units, and we want to get into which are n in terms of moles and r as a gas constant in terms of moles. And when you get into statistical mechanics, you're really thinking about individual molecules, right? And so I want to do the conversion there, get this r into k, where k is the Boltzmann constant, and its units are joules per molecule now, not joules per mole, joules per molecule per degree Kelvin, okay? And you can see what that number is. It's pretty small, 10 to the minus 23, because molecules don't have that many joules in them at the sort of temperatures that we encounter. So it's small. So let's see what we have here now. The new expression in terms of this n, which is the number of molecules now, not the number of moles. Big N is the number of molecules, versus little n, which is the number of moles. Which 1 mole is Avogadro's number of molecules, and Avogadro's number is a big number. And k adjusts for the conversion from moles to molecules. So here we have our wonderful entropy expression in terms of molecules and probabilities. Which is wonderful that we've come so far in this very let's say well, I was going to say rudimentary. Why not say that? We haven't put all that much thought into this, and we've made a huge leap forward in terms of our thinking. So I want to reiterate here. Note. Okay, let's do this. Whoops. Okay, I gotta grab my other one here. Note, delta Q from the plate is negative by convention when it transmits heat from the plate into the gas. So the change in entropy is positive. I said that before, because it's negative delta Q over T sub C, and delta Q itself is negative, so it's a double negative, which is a positive. So the change in entropy is positive. And I think that we've covered it there. Oh, net n times ln 1 over P2 is equal to, that's is equal to, right? Okay. I'm just seeing what this part on the bottom here is. Yeah, I just have ln P2 is equal to the change in entropy. Okay, that's fine. Oh, down here we say again, the change in entropy is equal to n times k times ln 1 over P2. And there it is in terms of probability. And this type of thinking was developed by a brilliant scientist, Josiah Willard Gibbs. And in 1902, he wrote a book on entropy, and he went through and derived statistical mechanics. So this type of thinking was given birth by Josiah Willard Gibbs, and we just kind of went through very quickly and did some of the thinking ourselves, came to that result. So let's see now. Right now we've done these other things. We've explored them. I don't want to talk in order to be timely. Let's jump here to apply the probability of definition of entropy and find the entropy of an alphabet of 32 symbols, and thus the entropy per symbol. Now, we have, in the English language, we have got 26 letters, and I wanted to include some of the other basic functions, and it might be like question marks and plus signs, things like that. I wanted to add another 36, another 6, so 26 plus 6 equals 32. And it also makes the chart that I'm going to do look a little bit more beautiful as well. So let's do that. Going to the next one here. And what we are doing, I'll move myself out of the way if I can. Use the example of the entropy of a letter in our 32 alphabet symbols. Okay, now if you look below, what I've done is I've taken questions. So on the first, up at the top there, you go, well, what we're trying to do is see what does it take to take those 32 symbols and put them in the right, like let's say these dots in the bottom were names of the symbol, like alpha, beta, right? You want to see what symbol. To put each of them in the right place to associate with the right name, you need to answer questions. So, which is, it could be just like what I'm going to do here. You start at the beginning, and then you say, well, for this particular letter, do I go left or right? And it says left. So we go down here. I'm going to use this thing up here. Start here, and we go left, okay? And then at this point, you got another option, and you go, oh, do we go left or right? So that's another question. Each question, left or right, is like one bit. It's like yes or no, or 0 and 1. It could be 0, 1, or 1, 0, whatever. One bit. So at this point where you see the number 29, is it left or right? And in this case, the right one is right at the beginning, that 1 down there. So we say you got to go left again. And then the 25th one here, is it left or right? It got to go left. Okay. And then this one here, number 17 there. Left or right? You got to go left. And down here, left or right, you got to go left again. Bingo, you put the first one in. Well, you notice that for every one of these letters, there's 1, 2, 3, 4, 5 bits. So I have 5 questions, 5 bits that needs to be answered. And we go through. Now, there's something interesting about this, but it's not horribly interesting. But if you count the number of splits, you go 16 and 17 up to 24, 25 up to 28, and then 29, 30, and 31. It's n minus 1. So you need to split the space kind of 31 ways through these questions. You need 31 of these questions. But what it is on anyone, let's just pick one. Let's go down here. Let's go down this one right near the middle. 1 question, 2 questions, 3 questions, 4 questions, 5 questions again. See, they're all 5 questions. So now I'm going to go up to again, talking about what it means, okay? So 32 symbols. It requires 31 splits to define each alphabet. I've showed you that. This means 5 question sheets of for 32 symbols, which means 5 bits per symbol. So we just figured that out just by looking at the chart. And we're going to use split things later a little bit too, and so it helps us to get used to what dealing with these charts with splits, two-way splits, which means we've got to use log to the base 2. So let's try that. Alternatively, the probability, we're going to switch to probability now rather than doing it by a diagram. The probability per symbol is 1 over 32. Right? You reach into a bag, pull it out, you've got 1 in 32 chance of getting a particular one correct by guessing, right? So then log 1 over probability equals log 1 over 32, which is log to the base 2 of 32. And you put that in your calculator, and it comes out with 5. Bingo! Wow! You get the same answer, which proves it's right, okay? So here I say, we get the same answer for both methods. Thus, we can also express entropy. You don't have to use logarithm of 1 over p. You can use number of bits required to specify a symbol through two diagrams like this. Okay, now this goes to show why I like to use 1 over the probability rather than just the probability. Because if you did when you do 1 over the probability is 1 over 32, right? It flips it, so you go log of 32, you get 5, which is the number of questions, right? It makes sense because it's given us the answer. Now, if you did log of p, the probability is 1 over 32. It's going to be a negative number, and you get 5, but negative 5. And when you go through a chart like this, you don't use negative 5 bits. So you can see why I want it in this. I'm James Bears. This is like James Bears convention. I'm sure there are other people who use it as well. But that's why I prefer this format. 1 over log. Log 2, in this case, is base 2, 1 over p. All right? So let's continue. Oh, now this one, when I thought of looking at this, listen to what it says, and it kind of scared me because it sounded really intimidating. We're going to derive Shannon's entropy and extend it to situations with conditional probabilities. Now, it's true that when he's doing his coding algorithm, he knew that when you have one word and you already have it, right? When you have decoded a message, and then you go to decode the next word, the value of the word before it in the English language affects the probability of the next word. I'm trying to think of something. Like if somebody said, Winston tastes good, maybe you're too young to remember that ad. But anyway, Winston tastes good, so the next word is most likely to be like a cigarette should, from the advertisement. And also, there's so many situations like that. So that's a conditional probability, where what the probability that follows depends on what came before. So when I started to think about it, it sounds so scary. But it turns out that same type of thinking that we've been using all the way along, where we work with the proportionalities and all that, it just, you go through it and you go, well, where's the difficult part? Because you're finished it, right? So we're going to do that next, and it's going to be kind of wonderful, I think. Okay, so what we're going to try to do here and achieve it. One, we're going to explain, well, exactly what is meant by the term of entropy. We've already done that, I think. We're going to use this definition, that's where we are right now, of entropy to derive Shannon's conditional entropy, which is the entropy contained within a digital message considering the effects of conditional probabilities, which means what came before, okay? And this is one of the cases well, not that few, but since I like to work, as if I was doing it originally, I don't normally pull things, but I like this little chart, and I got it from Shannon's original paper on this thing, and I don't have the link right now, but you can look it up. Shannon's original paper on entropy. And he has this little diagram there, and he says there's only one way that you can describe, like solve this, and it's his expression. And he says, if you can solve it, it's got to be this expression, which means conversely, if you do solve it, then you have his expression, right? Which is what I'm going to do. Right. So let's talk about this just a bit before we go in there. Now, the probability of this point right here, I'm not going to call this because I'm going to use it later. This is on the left, so I'm going to call it left-hand side, and let's make it bold. Then I'm going to call this probably right-hand side. Because they basically represent the same thing, the same probabilities, but in two slightly different ways. And I'll show you. The top leg is identical in the two. And the probability at this point here of getting whatever it is on the end is 1/2, because it's written there, 1/2. Same on this side. So far they're identical in format. But that's where it changes. The next node down has a probability of 1/3. Now in this case you can see that it has a probability of 1/2 from going to the point that I'm right now, that apex, down to this node here. Probably is 1/2. And then it has a probability going from the next node to the end node of 2/3. Now we know if they are independent, so we know that the total probability at this node here is 1/2 times 2/3. 2/3 is 4/6, and 1/2 of that is 2/6, which means 1/3. So it's the same probability as in the left-hand side. It's the probability, the conditional probability 1/2 times 2/3 gives you 1/3, which is the same. So in terms of probabilities, these two charts are identical for the first two nodes. Now, the probability for the next node down, the one on the bottom, is 1/6 on the left-hand side. And if you take the probability to get from to the almost near the bottom is 1/2, as you see, and then to get from that point to the bottom is 1/3. So 1/3 now is equal to 2/6, and you multiply 2/6 by 1/2, you get 1/6. So it's the same number. So these two charts are, from a probability point of view, the same, which means that when you make your expression for entropy, it has to produce the same entropy result for the left-hand side as it does for the right-hand side. And I don't know, it scared me when I thought about going and proving that. But it turns out to be so nice and simple. It's a kind of amazing. So we're going to derive Shannon's entropy in extended situations with conditional probabilities. That's this arrow, just to remind you where we're going with this. So for the pressurized cylinder, we got that the entropy is equal to a constant times the natural logarithm of 1 over the probability. And now we're deriving Shannon's entropy applicable to coding of information transmitting systems. And clearly it's not going to have the same constant proportionality as the constant for dealing with pressurized gases. But we will have a constant of proportionality that I'm going to introduce called Z, and it's just to take care of whatever the units are. Even when we talk about information theory, where we're using bits or qubits or larger chunks than bits, as a unit. So we can still have that. I also want to talk just briefly to get going here. that and by the way, we're deriving the Shannon theory for including conditional entropies. And I just want to show here that a little detail that we for people who are using their calculator, you might not have the log of the base 2 on your calculator, and I want to show you how we can convert that. And so the log to the base b of a, where a is any number, log to the base b of a is equal to log to the b to the x times log x over of a. Okay, now it's a mouthful, and I color coded the b's and xx so you can see when I convert to real numbers. So log to the 2 of a, which is what we're going to use here, to the base 2. But I want to show it's equal to log to the base 2 of 10. That's your conversion constant, times log to the base 10 of a. So, and I give you an example of where I just take the log of base 2 and of 10, and you get this number here. Well, that's a constant. So you can convert log to the 2 of a to log to the 10 of a by applying that one constant there. And in this case, 3.32, blah, 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 that number. So that could be sometimes when you don't use the base 2 and you want to use base 10, you can use this conversion constant of proportionality. To form that conversion for you. So I just want you to know that. Now we're talking right now about Shannon's theory of with including the effects of conditional entropy, and you know the problem with these proofs are that they're so freaking easy when you think about it and just look at it. That yeah, it's just kind of I don't know, anticlimactic in some way. So let's do that. Let's look at these things. And we know from the left-hand side, and comparing that to the right-hand side, that if we just, for every branch on the right-hand side, because the left-hand side is very explicit, there's no branching other than the 3 branches, and we have the probabilities for those. So that one's pretty explicit. But this one, to make the right-hand side in terms of probabilities and the same as the left-hand side, you take the total probabilities, which includes the one in the last branch, which in this case 1/3, and find out what the probability is on the entire branch. So you do, for example, 1/3 times 1/2, and that gives you 1/6. Right? And you take 2/3 times 1/2, and that gives you 1/3. And so when you by doing these, multiplying the probabilities along the entire branch for every branch, you can convert the situation from the right-hand side into the left-hand side. So we can do that as follows, and I have written here, James Bears' concise derivation of Shannon entropy. I'm James Bears, so my name's in there. Normally don't do that. But here we go. Multiply across by all the probabilities along the entire branch. And so that would be, the contribution there to the total entropy is proportional then to the probability along the entire branch. Like I just said, you multiply all the probabilities along the branch from the end to the beginning. So you get probability of branch per this particular branch times the log of 1 over that probability. So it's very similar. You have 1 over the log of probability is the entropy, and the frequency of the entropy is dependent on the probability. So its contribution to the total entropy is proportional to the probability of the entire branch times the log of 1 over the probability of the entire branch. Okay, And then you, for number 2, you just perform the summation to get the total entropy, right? So because in part 1 here it was the contribution of the total entropy, and this second one here is the total entropy is going to then be proportional to the sum of all of the contributions. So you sum these individual contributions here, and that's what I've done in this expression. Okay. So 3, apply the constant of proportionality z. I just pulled that out of the air. I didn't want to use k or r because they're already used. So apply the constant of proportionality z to turn the proportionality into an equality. So the total entropy, and this is Shannon's entropy, is going to be is equal to z, the constant of proportionality, and might have to do even with this something as simple as converting the log 2 to log 10 times the sum from I equals 1 to n, where n is the total number of these branches, times n, 1 to n, and I have the proportionality that I need to take that out now. I'm turning it into an equality. Boom, gone. So it's equal to z times sum of 1 to n of the total probability in the branch times the log of 1 over the total probability in the branch. Okay, so yeah, and here's the conversion. We talked about that earlier. So now we just derived this by looking at these two charts, and right-hand side and the left-hand side, and we came up with this result. Now, Shannon wrote in his treatise that he published in 1940 on his entropy applied to communication systems, and he had an equation like this, and he said that if you get the correct equation, there's only one that will work for this particular type of diagram. And conversely, I would say that if you perform the calculation and you find out that the entropies on the left-hand side are equal to the entropies on the right-hand side, as it must, because I say here, the system probabilities on the right-hand side are the same as the system probability on the left-hand side. Thus, the entropy calculated for the right-hand side must equal the entropy calculated for the left-hand side. So if you calculate those two entropies for the right-hand side and for the left-hand side, and they're equal using this expression, then the expression is correct. So we just derived this expression so easily, yeah. So the next step then is to perform a calculation here, test this new derivation on an example. So let's do that. Let's actually calculate it. And again, we're trying to see, make sure that the entropy calculated for the left-hand side equals the entropy calculated for the right-hand side. So let's do the total entropy for the left-hand side. All right. And now I'll just remind us that, this probability BI is the probability along the entire branch I. Okay. So on the left-hand side, here's that expression, and it's going to be this. So left-hand side is very simple because there's only one probability for each branch, right? And there's only one segment of each branch. So it's going to be the old one where it's 1 over the probability times logarithm of 1 over the probability, okay? So for this first branch here, 1/2, the probability is going to be 1 over 1/2, which is 1 over 1/2 is 2, right? So it's going to be log 2. And then the probability times the log over 1 over the probability, which is 2, is going to be 1/2 times log 2 of 2, right? And then the middle leg here, the probability contribution for that, the entropy contribution of that is going to be log 1 of the probability, which is log of 1 over 1/3, which means log of 3, times that probability, 1/3 times again. So it's 1/3 times log the base 2 of 3, right? And lastly, on the left-hand side, we have a probability of 1/6. So it's log the base 2 of 1 over that, which is 6, and then you multiply it by 1 over 6, again, the probability, and you have that. So I went through and I calculated, and my particular calculator does have a base 2, log to the base 2. So I get these numbers here, and I add them up, and I get this specific number, and this is funny. Notice I got K there. It's Z, because you don't want K, Z, okay. Just a constant of proportionality that could be many things. It's basically to clean up the units and make everything make sense physically. Okay, so that's the left-hand side. We got a number. Now remember, the entropy on the right-hand side, when you calculate that, if you have the right expression, it should equal the entropy on the left-hand side. So let's test that out, right? So apply the expression that we derived right here. And in this case, on the top, on the right-hand side now, we move from the left-hand side to the right-hand side. The top leg is the same as before. So it's going to be 1/2 logarithm to the base 2 of 1 over 1/2, which is 2. Okay, so this one we've done. So now we're going to go into the next one, which is this leg. And the probability in front of the log is going to be the probability along this entire branch, which is 1/2 times 2/3. 1/2. Oh wait, I'm not doing that branch. I'm doing, of course, the one in the first branch is this one, right? Which the probability of that entire branch, right from the end to the very beginning, is 2/3 times 1/2, right? So we put that in front. And this is for the second branch. So you have 1/2 times 2/3. That's the total probability along the entire branch. And then the log the base 2 of 1 over that. Now 1/2 of 2/3 is 1/3, and it's 2/3 is 2/6. So 1 over 2/6, 2 over 6 is equal to 6 over 2. So there it is right there. That's the middle branch, okay? Now let's calculate this last branch I'm showing here. And the total probability that goes in front of the log is going to be 1/2 times 1/3. There we got it, 1/2 times 1/3. And 1/3 is 2/6, so 1/2 of that is going to be 1/6. So the 1 over the probability is going to be 6, okay? And so I calculate all of that out, and I get these numbers, which are actually the same as these numbers, and you add them up and you get the same result. So, yahoo! The entropy calculated for the left-hand side equals the entropy calculated for the right-hand side. So we tested our derived theorem for the Shannon, including the conditional probabilities, and it works perfectly. So that's magnificent. It's we have another success, and it came out so easily. It's hard to, blink and you miss it, sort of thing. So this brings us to the point where it would be useful to provide a little bit of a historical summary of what we've accomplished today. And at the top here, we see we first went back to 1850. Where Rudolf Clausius developed his theory of entropy. He was the first one. And he came up with the expression that the change in entropy is equal to negative the change in the heat transfer across a boundary of constant temperature. Okay, so that's number one. And then we went through and we derived from that, where entropy was in terms of of heat to Josiah Willard Gibbs' view, where entropy was expressed in terms of statistical mechanics, which was basically expressing entropy in terms of probability. And we were able to convert, as a transition, the entropy from Rudolf Clausius into an entropy similar to Josiah Willard Gibbs' version, and in which entropy is equal to n times k, where n is the number of molecules now, because when you're thinking in terms of statistical mechanics, you're thinking of molecules in motion. So n is the number of molecules times the universal gas constant of Boltzmann times the logarithm of 1 over the final probability, or the probability of these states in their current condition. So that's Josiah Willard Gibbs around 1902. So moving forward in history, we also took the formulation of Josiah Willard Gibbs, and we did as Claude Shannon did, expressed explicitly entropy in terms for a binary message, including the effects of conditional probabilities. And what we came up with for this one was that entropy, total entropy, is equal to the sum of, Z, which is a general constant of proportionality, to convert an expression in terms of proportions into an expression, inequality. So we have Z times the sum of all of for each of the branches in the system. The sum of the probabilities along each branch times the logarithm to the base 2 of 1 over the probability of the entire branch. So those, you take the contributions from each one, you add them all up, and we get this expression from Claude Shannon for entropy, and he came up with that around 1940. So, right, now let's delve down a little bit more deeply, and just as a final summary of where we've been and how we got there, so we can just sort of hold the story in our minds rather than not knowing how we get there, you know. Usually at the end of a presentation like this, you realize what's going on, and then you may walk away and you're having a coffee or something with somebody and you go to talk about it, and you can't remember the story. So I'm going to piece that together in brief in this chart we're looking at. A review of what we accomplished. So here's what we wanted to do, and this is the same list I gave at the beginning. We wanted to explore the mathematical parallels between exponentials and probability, and we did that. Then we wanted to equate the probability to equate probability to exponentiation, and solve for the exponent x. So what's x? That allows the expression of probability to be in terms of exponent, and then the exponential e, and the logarithm. And we found out, and probability. So from exponents to probability, how do we make that connection? What is x? And we found that p of x is equal to e to the natural logarithm of x. And it kind of made a lot of sense, actually, because they're anti-functions, and it proves x is, I should write it here. P to x is ln of p of x. That's funny. Should I have, yeah. Okay. So, yes. The probability of x is equal to e to the natural logarithm of p of x. So that statement is kind of an obvious statement. Okay. Then we wanted to define an application for that situation in physical reality, and we found one in terms of having a piston and having a plate underneath at constant temperature, and having a graduated cylinder filled with liquid dropping, and the graduated cylinder is getting lighter and lighter, so the piston is expanding and expanding, but keeping the same temperature at constant temperature. And from that, we were able to do what we wanted, derive Rudolf Clausius' thermodynamic formulation of entropy in terms of both heat transfer at constant temperature and equivalently in terms of probability. So we found Rudolf Clausius' expression, which was the entropy is equal to negative the change in heat over constant temperature. And then we're able to do a transition to express that same expression for entropy in terms of probability, moving into the world of statistical mechanics and Josiah Gibbs, okay? And then we wanted to apply, I'll move the arrow here, the probability definition to, in terms of entropy, to find the entropy of an alphabet of 32 symbols and thus the entropy per symbol. So we did that. We found out for 32 items. Remember that it was a splitting tree and there are 31 splits. But it worked out to be 5 questions, 5 binary questions needed to be answered for each of the symbols to put them in the right place. So each of those symbols, remember, had 5 bits. So that got us used to thinking in terms of bits and symbols and entropy. And we were ready then to derive Shannon's entropy and extend it to situations with conditional probabilities, where you have probabilities along the segments of branches from beginning to end. And then we wanted to test this new derivation on an actual example and to make sure it works. And we did that, and it worked perfectly. All right. So this was very exciting, and speaking personally, I found it so the proofs came so quickly and easily that it's giving me an appetite now, because what I want to do next is make a presentation on quantum systems and apply the same kind of thinking that made the entropy from classical mechanics and then from statistical mechanics, and then from that made it so easy also for Shannon's work with coding of information systems. I would like to apply the same kind of thinking for quantum mechanical systems, and hopefully to have results and proofs that are equally concise and comprehensible for quantum mechanical systems. And I actually know the answer. I know that we can actually achieve this. So that's what I'd like to do in the next presentation. Stay tuned. And I would like to say at this point, thank you very much. This has been a wonderful experience, having the privilege of presenting this. And stay tuned for the next one. Bye now.